Yeah, I guess. Yeah, thanks for reminding. I think now it is on. Anyways, I mean, whatever I just mentioned until now, it was I had already discussed this in the last class. Now the question. So, are there any questions until here? This is what I covered until last time, and then I proceeded to ask some of the questions one is interested in. And one of the first questions that I would like to understand is, will the disease spread? Right? That is the first question that one would be interested in. Question 1. Will the epidemic or whatever infection spread? That is the question we are posing. And that means this question is equivalent to saying that right at the onset, that means whenever you are starting, let's say that is your starting point of t equal to 0, when your total number of infected people is I naught and the number of susceptible people is whatever S naught, these are the initial conditions. Then you are at that point of time is if you find out the derivative of the number of infected people with time, if di dt of I is greater than 0, then S is equal to S naught, I is equal to I naught. That means basically what you are saying is, let's say that initial condition I am denoting by t equal to 0. If this is true, then the disease spreads, then infection spreads. Conversely, if this derivative were negative, then you would say that the disease is not spreading because you know the number. That means if you evolve the number of people according to this differential equation, if the derivative of I with respect to time were negative, that is going to tell me that means the number of infected people is coming down. Right? So if it comes down with time, that means eventually you can imagine that after some later time, the number of infected people will decrease, and so you will say that in that case the disease is not spreading. That means it is stopping. Although there are infected people, the number sort of dies down. So this is the condition. Now, if you look at this equation, that means if I call equation this is 1, 2, and 3, that means I have to set, if I impose this condition, what it means is, that means you look at the right hand side of equation 2. This is just telling you R S naught minus A. This quantity is greater than 0 for infection to spread. Okay. And in other words, I is some non-zero. I is a positive definite. It's the number of infected people, so it's positive definite. So the only way this can be greater than 0. So basically, the condition is on that R S naught minus A is greater than 0. And if I rearrange that, then I mean, if I pull the A on this side, finally what you would get is R S naught by A has to be greater than C. I will define some of these things. This quantity I call as R naught.
Excuse me, sir.
Sorry?
Sir, in the last equation, there should be 1 instead of 0.
Sorry, exactly. Thank you for pointing it out. I was making a mistake. Yeah, thanks for that. Please note the correction. So, I mean, this condition, so you bring A on this side and then bring it on this side. So then it has to be greater than 1. Please make it. R naught, and I'll explain these terms. But just first let me write down what it is. This thing is also called basic reproductive number. This ratio R by A is also called contact ratio. So first I tell what physically it means. This first number, which is basically the ratio of this, see that's that rate constant which sits in front of equation 1. So this ratio of R by A is basically telling you the fraction of population who are coming in contact with the infected people. So that's why it is called contact ratio. That so if the contact ratio is high, that would mean a larger fraction of people are coming in contact with infected people. So that is this number. Finally, this number R naught. In fact, if you have followed the news related to corona or wherever they are discussing the data, this is one number that they say. That when do you say whether what is the status of the disease, whether it is spreading fast or not, is categorized by in terms of this basic reproductive number. Physically, what it means is that on an average, if 1%, how many people are getting infected from one individual? So if R naught, you can imagine if R naught is greater than, if R naught value is very high, let's say R naught value is 3. What it would mean is that on an average, one infected person is spreading the infection to 3 different individuals. That is the meaning of this word R naught. So obviously, I mean, this is in some fraction, and in similar spirit, if R naught is less than 1, like I told you, that in that case, the disease will not spread. So as far as this disease is concerned, this R naught and this contact ratio is also called Q. So if you think of this condition, equivalently, what the condition is that R naught Q has to be greater than 1 or R naught has to be greater than 1 for spread of the disease. And yeah, so this is the meaning of these quantities. Now you see that already we have many of the measures. You can ask that how does these parameters Q or R naught, how does it change on various circumstances? So when we are saying, so for instance, in the case of corona, when you are said that you wear the mask or as far as possible maintain physical distancing, you do not come in contact with people at close distance. Effectively, what you are reducing by such measures is you are reducing this value of Q. Remember, the disease will spread when R naught is greater than 1. It has 2 parts. One is this Q and one is S. So the effect of maintaining physical distancing or the fact that you are wearing mask, people are wearing masks, is that means whenever you are coming, even when you are coming in contact, you are effectively reducing this contact ratio Q, the value of contact ratio Q. So you are helping in effectively reducing this whole number R naught, because part of that is this. What about when people say that, oh, the solution of this disease is finally when vaccination will come? So one can ask the question, effectively, when there is, let's say, much large scale vaccination, what does it affect? Does it affect Q or does it affect in here the S naught? If you think a little bit, you would realize that moment you have a vaccine, let's say in some future day you have some vaccine, and then so when you have a vaccine, those who have taken the vaccine, assuming that the vaccine is good, that means that fraction of population, let's say 50% of the population have taken vaccine, then those 50% of the population no longer belong to the category of susceptible population. That means if you have taken vaccine, even if you come in contact with some infected person, you are completely immune, you will not get the infection. So effectively, that means you are changing the value of your S naught. So, so many of this, the value of this kind of modeling approaches, it gives you certain insights that what kind of strategy should one adopt to control this kind of spread of the epidemic. So in here, for instance, the main aim is that somehow you have to bring the, this basic reproductive number R naught down below 1 in order to prevent the spread of the infection. So these are, I was just giving you an insight that how various different measures that we implement at the level of policy for the entire population is going to is described in terms of these numbers that you see emerging from the model. So this was the first question. Next
question. A question.
Yes, please go ahead.
Sir, does the availability of a vaccine change the rate of recovery in the equation?
Not really. See, if it is a vaccine, what does a vaccine do? In principle, suppose, meaning even traditionally, like when you take polio vaccine, when you were whatever, you don't remember, but whatever, when your parents helped you get polio vaccine. Moment you take a vaccine, you are not even susceptible to infection. That means you take a vaccine, you will not get infection.
Right.
So if you do not get infection, see these equations, if you write down, when I say susceptible population, that means who are susceptible population? That means I may not have got the infection, but I have the potential of getting the infection, right? Whenever I come in contact with an infected people, I have a finite probability. But one moment I have taken vaccine, I am completely immune. So my initial, so when you are writing down these initial conditions that you I is equal to I naught, S equal to S naught, effectively, let's say 50% of the people have taken vaccine. That means those 50% are not even if they come in contact with infected people, they'll not get it. That means here effectively your value of the number of susceptible people has now become S naught by 2. So in that sense, vaccine affects S naught, not really the contact ratio. Is it clear?
Okay, sir. Thank you, sir.
You can argue, like, see, for instance, I mean, until now, people at least do not know conclusively if anything improves your immunity. And no one really knows. If someone is saying anything, those are fake. But let's say there is some disease where, if you take something, your immunity increases, relatively increases. That would mean that even if you come in contact with some other person, your effectively the rate at which you catch the infection is reduced. That means the small r is reduced. In that case, you are tinkering with this. Or even when you're actually wearing a mask, or you're keeping physical distance from someone else, you are essentially reducing your effective value of R. Right?
Right. Yes.
Yeah. Okay, so then I'll proceed. So the next question that one can ask is that, okay, what is the, when the disease is spreading, what is the nature of initial increase of R? Even as a physicist or as a mathematician, what is the functional nature of the initial growth trajectory? That means, how does the number of infected people grow as a function of time? So for that, so let me write down this second question. Question 2. What is the initial nature of growth of infected people? I is of course infected. So I want to find what is sort of the initial time temporal behavior of how the infected number of people are going as a function of time. What kind of function it is. For that, you again look at this equation. Now, again, try to imagine what would be the initial situation. Right at the beginning of the disease, in fact, even though your initial condition is S is equal to S naught, I is equal to I naught, at the beginning, I naught is some small number. And most of the people are actually S naught, like they belong to the category of susceptible people, and I naught is like very few infected people are there. And you want to find out what is the nature of growth of this total number of infected people. Let's say you have started with 10 infected people over course of time. How does this function grow as a function? You notice, so that means I take a more closer look at equation 2. in principle, when I have written down these, of course, you realize that S is a function of time, I is also a function of time, R and small r and A are, of course, constants which we have taken. But these are functions of time. But you make an assumption that during the initial phase, as the infection starts spreading initially, of course, my total number of susceptible population, that will change. Let's say you had started with 10,000 individuals who are susceptible, there are 2 infected individuals. This 10,000, as you see, some of this 10,000 will become infected. So the S which had started from 10,000 will reduce to some number, let's say 9, let's say 2 infected people happen over some period of 2 days. So number of infected people. So the S has changed from a value of 10,000 to 9,998. Point I'm trying to make is that this initial period, the S value, of course, technically it will change, it will in fact reduce, but you can pretend that this S, let's say, remains almost constant. Whatever, S remains almost like at the onset. S is nearly equal to S naught. That means you are sort of pretending that although it is a function of time, and you are pretending as if S is just a constant, which is this S naught, whichever was the initial starting value. If that were so, you go back to, in that case, you go back to this equation. So your initially, that means during this onset, this could be the form of your equation. Right? You have replaced. Now you look at this equation carefully. So that means at the onset, now you can take this R S naught minus A step. Now this equation, many of you would be able to recognize. What kind of solution will it give you? Can you see this and tell me?
Exponential.
Exactly. So you can see this, that moment you have this, I remember is a function of time, like the usual, di by I is equal to R S naught minus A. I mean, this is rather trivial, but you should be able to do it. Once you can easily separate out the variables, you're able to do it because you are treating this S is equal to a constant. So you can take this R S naught minus A out of the integral and perform the integration easily, which you wouldn't have been able to do if your S was some function of time. This you should keep in mind. You are able to do it only because you are saying at the onset S is almost a constant. And because you are able to do that, you can, of course, integrate. And the solution that you get is, that means your I as a function of time is almost equal to, this is at the onset, is the constant I naught, exponential of R S naught minus A into time, right? I can sort of rearrange this equation if you like. I can write it . You can, so this I of t you pull out a factor of R S naught. Yeah. You pull out a factor of, okay, you pull out a factor of A. And then you are left with R S naught by A minus 1. And then you have that. And this quantity, R S naught by A, we had defined in terms of this basic reproductive number R naught. So this I of t at the onset is approximately I naught exp A R naught minus 1. Okay. you can clearly see that at the onset, the nature, so that means how will the initial trajectory of I versus T look like? You start with some small number I naught. If your R naught is greater than 1, then it will have an exponential rise, right? It will grow like this. So there is an increase, exponential increase of the number of infected people, at least during the initial phase of the spread of that. You can, from this equation, you can also see that if your basic productive number R naught were less than 1, then if it were less than 1, you see this whole thing will become negative. Then you will have I naught exponential of some negative prefactor times time. In that case, so this corresponds to R naught greater than 1, whereas if R naught would have been less than 1, it would have been decaying. You would have got a decaying solution, or in other words, whatever we just mentioned earlier, that the infection will not spread. I also, so those of you who are interested, you can actually, I don't know if you have kept track, one of the websites where there is in fact a lot of data for all the different countries, including India, but basically all the different countries, that you'll have here this discussion going on, that we are having this exponential rise in the number of infected cases during the initial phase. And in fact, even if you go to this, one of the sites is this one. .com or org, I forgot. But basically, it has the data, so you can actually go back and see the data for individual countries. And in fact, you will notice that, for many of the data, you will have this thing that you can actually plot those data in log scale. That means you have the number of, so in terms of terminology, when we say infected, currently infected, that means basically the active cases. Right? There is one which is the total number who have been infected. IT in our language is the number of active cases which are there. So you can go, for instance, to the number of the initial rise for the data of China or even India. You would notice that many cases it actually fits very well with this kind of exponential growth pattern that I just discussed. You can actually go and play around with the data. The data is there. How do you check? How do you, for instance, if you want to verify whether it is an exponential growth or not, it's rather simple, right? You have the total number of, you have function of this time, one axis is time, whatever, starting from February, March, etc. And the other axis, the y-axis is the number of infected people. So if you take log, if you take the log of this thing, you know that, if you take a log of this, if it is an exponential function, that will give you a straight line. So if you see that, if you take the log of the data and you plot it, if you get a straight line, and from that you will be able to actually also extract whatever is the slope. That means you'll be able to extract the slope of that straight line in the log plot is going to tell you what is the growth rate, which is, it's going to tell you what is A into R naught minus 1. So this is something you can go and check with this worldometers and get back and tell me that whether you actually see this game. So this is the second characteristic that you, second question which we have addressed within the framework of this model. Okay. Now, what other questions are there of interest? So the third question, which we can ask, and one would in general be interested in such kind of diseases, that what is the maximum number of infected people that would be there for a particular disease? So before I actually, meaning I'm not solving the equation. In fact, part that you have to do is that since these are differential equations with certain initial conditions, you have to actually go back and see for different initial conditions what kind of solutions of S, I, and R Do you get? But without going into showing, I'm just plotting some of the typical behavior. So if I had plotted S or S as a function of time or I as a function of time, how it would look like. So let me plot typically, how the infection will behave. So initially you will have some number I equal to I naught. Typically, if R naught is greater than 1, what would happen is it will grow and then it will reach a maxima and then it will come down. This would be the behavior of I as a function of time. So how S will behave? One second. The number of susceptible individuals, on the other hand, would always, I mean, it will start with some value of S naught, it will keep on, decreasing as a function. And if you look at the recovered people, the number of recovered people will initially, let's say, it starts from 0, it can only go on, keep on increasing. All the while, you must remember that because we are saying that the total population is constant, what would always be obeyed is initial number of infected people and susceptible people will always be equal to, at some any given later point of time, would be equal to R of t plus S of t plus I of t. This is as far as this thing goes. But now that you see this curve, one of the things which would be of interest to spreading the disease or managing or tackling the disease is that what is the total number of infected people? That means, what is this I max? That means at any given point of time in future, what is the total number of active infected cases that one would be having? This is a very important question, no? Because as the disease spreads, so for instance, this disease is spreading, you would be, any government or any organization would be constrained in knowing how many hospital beds are required, how many oxygen cylinders are required. All these questions is linked. That means you should have an estimate that at any given point of time, what would be the peak value of the infected number of people. And all the while you're hearing this discussion, no, that we have still not reached the peak. That means basically we have still not reached the stage where I is equal to, like I said, that typically it will grow like this and then it will fall off. And you also heard of this statement, how do we flatten the curve? Why do you want to flatten the curve? The reason is simple, because if the curve is suddenly very sharp, that means at any given point of time, you will have large number of people, and then you will have constraint because you may not have enough hospital beds or enough number of doctors, all these things, or enough number of supply of ventilators. And in that case, the treatment would be bad or you will not be able to manage the disease. So one of the questions that is important to know is to answer this question, that what is your I max? That is, what is the maximum number of infected people?
So di by dt equal to 0?
That I just discussed. No, so that's the condition. Correct. So I'm saying if I have to find out, you correctly pointed out that that is the condition when my I would be I max. Your knowledge of derivative tells you that when I is equal to I max, when at I equal to I max, if you take the derivative of I with respect to time, that has to be equal to 0. Okay? I agree with it. But finally, you have to find out that I max, right?
Yes, sir.
That's what we are after. So I agree that that's the condition, but we actually want to find out what is I max. Maximum number of infected people. Okay. So for that, you again, let me write these equations. Again, we are running out of time, so I'll certainly just quickly finish and repeat next time. Let me write down the first two equations quickly. These are the first two equations involving my susceptible population and infected population. Okay. Now divide equation 2 by 1. Okay. Divide 2 by equation 1. On the left hand side, what you will get is partial derivative of I with respect to S, and on the right hand side, you will have -1 plus A by R. Okay. I hope I have not missed the sign. Yeah, so this would be the. Now, this equation you can integrate by separation of variables rather easily. So, I mean, basically what you do is di, that is di is equal to ds, and now you integrate it. Integrate both sides. If you do that, so are the steps clear up to here? I hope. So once I integrate this equation, so let me call this equation 3. What you will get is left hand side, and remember, I'm using the condition that initially my I at time equal to 0. So I'm integrating between initial time and later at some time t. And my initial value of I is equal to I naught. So I at some meaning, yeah, left hand side will S minus S naught, and this thing you recognize A by R. So R by A is defined as Q, which I had defined earlier. So basically what you are having is 1 by Q, and when you integrate log of S, it will just give you. Okay. This is the solution of the differential equation at some given point of time. Now we are interested in the question. What is I equal to I max? When I is equal to I max, that means when as you rightly pointed out, in that case, ddt of I is equal to 0. And ddt of I is equal to 0 would mean that the right hand side of this equation 2 would be equal to 0. That means my Rs minus A is equal to 0. Or in other words, my S, which is, let's say I'll call S at this I max, this is equal to A by R. That means the value of S takes the value of 1 by Q. Okay. So that's the step. So now what I'm going to do is that at I equal to I max, S takes a value of 1 by Q. I'm going to substitute that value of 1 by Q back into my original equation. That means, let me call this equation 3. And this fact that I got by imposing this condition of I max, that the derivative of I with respect to time is 0. The condition that I'm getting, I will substitute this value of S back in equation 3 and see what comes. So the moment I do that, so let me on the right hand side, what I'm yes. So I max minus I naught is equal to S. Like I said, S has now become 1 by Q. So minus 1 by Q plus S naught plus 1 by Q log of S minus This has again become 1 by q. So basically log of q by 1 minus. You can bring the I naught in this side. So let's say right hand side you have I naught plus S naught, and on the right hand side so I'll take this factor common. So let me just put everything. So I max is equal to S naught plus I naught, and then you have okay. If it is not very clear, let me write it more. Fine. Let me rewrite this. I could have also written it as let us call this number S naught q is equal to x. Thing that I want you to notice is that this I max has two parts. First part is what? It is I naught plus S naught. That means the initial total population which was there, that population, and then you are subtracting out this bit. Right? Now this bit, maybe we are in a hurry. Next class I'm going to show you is that this extra bit that you see here, if you plot this function, that means if you plot this function 1 plus log x by x, and you remember that if your infection spread is high, that means your value of q is high, then you would realize that this number would be a very small number. So in fact, what SIR model tells you that if your q value is very high, then the maximum value of the number of infected people at any given point of time can literally be almost be the entire population. So we will discuss in next class, next Monday, better on these aspects and other aspects of this model. For today, I will stop here. So if you have any question, you can ask. So I'll just summarize how the last question that I posed. The last question that I posed was that at any given point of time, what is the maximum number of given maximum number of infected people? So the way I proceeded with the problem is I looked at the first two set of equations involving I and S. I divided the second equation by the first equation. That gave me the solution for this differential equation corresponded to I as a function of S. Then I invoke this condition that at I equal to I max, my ddt of I is equal to 0. And the consequence of setting ddt of I is equal to 0 gives me a value of S which should be equal to 1 by q. I substitute it back into the solution of this differential equation to finally arrive at this form. And this is something which I'm kept the explanation for later. I'm going to show that that last term is a small term which allows us to conclude that the number of infected, maximum number of infected people is going to be very large. Okay, so I'll stop here unless you have some specific questions.
Sir, one question.
Yes, go ahead.
This S naught over x 1 plus n in x.
Yes.
Is that RT?
No, this is, see, finally it would be some number. This one.
Yeah.
Whether you will, I mean, I will not directly relate it to R of t. I mean, right now, that's not what we are after. We are not after what is the recovered. I have to see whether this also corresponds to this. Right now, I just want to argue and want to check what is that maximum number of infected individuals. All I'm saying is rather one has to analyze how does this particular function behave as a function of Q or S. That's what we would like to address in next class. And I'm going to show that that is going to be small.
Thank you, Steve.
Hello, sir.
Any questions? Yeah.
In the current situation of corona, which rate we will consider as the correct information about this pandemic, the death rate or DI by DT, infected rate?
No, correct meaning depends on the question. No? Meaning death rate, of course. See, I'm saying corresponding to infected, not all people are dying. First of all, I must warn you that this model is not the correct model for corona. Corona is way more complicated than this. Many of the assumptions that I had said, like all this A, B are constant, that it does not depend, those are simply not correct. Okay, so let's just be blunt. This model is not for corona. It only gives some qualitative idea on how you go about it. I mean, one thing I can certainly say that, you know, in TV you keep on hearing, oh, our recovery rate is very good and all. That is all nonsense. That is just propaganda. And see, I mean, the numbers are there in front of you. I mean, the number of infected people has been growing. How does it mean? Recovery rate doesn't depend on the policy, right? I mean, if you are a younger person, that is a common sense that, you know, the older people are more susceptible to death than younger population. India has a much more younger population. So thankfully, because our demography is such that the, you know, the overall population in India, more than 50% or maybe 70% of the population is below the age of 50. And that's why the death rates are lower because of the nature of the disease. That has nothing to do with the, you know, the policies that have been taken to spread the disease. But one thing is clearly true that, you know, the scientific temper in our country is missing. We have not analyzed the thing, or we have spent our time on stupid things, which has not allowed us to objectively find out what would be the solution to the disease. And that's why we have, until now, we have not been able to successfully combat it. That's a very unfortunate thing. I hope that we all as a society will learn and try to correct this mistake. Yeah. So I'll stop here. I would say that there is, whether you look at the death rate or the number of infected depends on the question. I mean, finally, of course, death is more important than whether people are dying or not. But the reasons for why death is low and low or high depends on a number of factors. It is not a very simple, straightforward answer. Definitely, I don't know. Okay. So
Sir,
I think.
Is it possible that?
Yes.
Sir, is it possible that if we do nothing, then also DI by DT will